Hey folks, working on class number 63. It is the last class for the quiz, and we're going to calculate some potential energy in springs and practice conservation of energy with springs. So as far as calculating the potential energy in the springs goes, it's really not that bad. Potential energy in a spring equals 1/2 kx squared. Potential energy is still measured in joules. The spring constant is newtons per meter. The spring elongation or compression from its natural length is x. Don't forget, only the x is squared. You'll frequently hear this referred to as elastic potential energy. All right, that phrase can be confusing. I always call it potential energy in a spring, and even on your reference table, it has a subscript S for spring. Now, one thing I mentioned in class, and I think it's important, is to recognize how similar in structure this equation is to the kinetic energy equation. That one was 1/2 mv squared. This is 1/2 kx squared. So there are some similarities there to just be mindful of. So we practiced just doing some calculations here. Overall, these are, I hope, pretty straightforward. You definitely have to practice them though. There's some order of operation mistakes you could potentially make, or things you could forget to do, or lose your square here. So definitely practice these, but hopefully these weren't too bad. All right. All right. Now for this one, here's a spring going back and forth. All right, or a mass going back and forth on a spring. So it's picture. It's try to imagine it moving back and forth on the spring, like back and forth, like oscillating. So notice how the total energy of the system is the same the whole time. Whether the energy is potential in the spring or kinetic, it's kind of going back and forth and always equals the same total number. The other thing I want to draw your attention to is how whether the spring is compressed a certain distance or stretched a certain distance, it has no effect on the potential energy in the spring. Because think about it, whether x is a positive or a negative number, it's squared, right? So it doesn't really affect the energy of the spring. So from what we can tell, x is no different if the spring is compressed or stretches, or as far as energy is conserved. Or excuse me, as far as energy is concerned, okay, there's no difference between compressing and stretching a spring. Okay, the energy equation would still be the same. It's just an important thing to keep in mind. All right, so this is an old Regents question, A and B, so make sure you're pretty comfortable with this. So the first one, finding the elastic potential energy stored in the spring. Hopefully that's not too bad. 1/2 kx squared. You're given k is 50, you're given x is 0.1. 1/2 times 50 times 0.1 squared, only the 0.1 is squared, you get 0.25 joules. Most people had no problem with that in class, so I'm not going to go through that too much. The next one is really where I want to focus, and well, let's just get to it. All right. So I purposely kind of left everything here because there's a lot and I didn't want to forget anything. So first off, we're neglecting friction, so Q is 0. Okay. The other thing that is not so obvious in this question. All right, so let's see what's happening here. The ball is stored and the spring is compressed. Then the spring decompresses and the ball is fired. All done horizontally. All right. So just think about that. The ball is compressed. The spring is compressed. The ball is at rest, and then the ball is released. The spring is released. The ball shoots off. So we have to go through a bunch of stuff here. So we have to set up our conservation of energy formula. So write that down. PESI plus PEGI plus KEI plus QI equals the same thing, all fine on the right side. Notice how we're now adding spring potential energy. It's like another term. You only need to add it if this is a spring question. So all the Q's go away because there's no friction here. So, okay, we're down to 6 terms. Well, why the heck did I say that the potential energy, why did I say that the gravitational potential energy was 0? Okay, think about it. Why is the gravitational potential energy 0? Okay, well, it's actually not 0. Here's the deal. The initial height and final height are the same because it's fired horizontally. Therefore, no matter what value the initial gravitational potential energy is, the final gravitational potential energy will be the same. Thus, they cancel out no matter what, because they will always be equal to each other. All right? Maybe not entirely obvious, but you kind of get the idea. All right. Now let's look at the initial kinetic energy of the system. All right. Now, the initial kinetic energy of the system before it's fired is 0. Okay? Because the initial velocity is 0. Okay, so the only thing you're really left with on the left-hand side is the initial spring potential energy. So let's cross out everything else. Should have crossed those out before. So that's fired. Let's go to the final side. Okay. So why the heck is the final spring potential energy 0? Well, because the spring decompressed. So that becomes 0 as well. So all we're left with on the right-hand side is kinetic energy. So basically what happened was the potential energy in the spring turned into, sorry, I'm having some trouble scrolling. The potential energy in the spring turned into kinetic energy. Okay, so the initial potential energy in the spring was equal to the final kinetic energy of the system. That's it. So if you were, if the Regents exam was showing, if you're looking at their answer key, they would just jump to that and say, the potential energy in the spring turns into kinetic energy in the ball, done. And you just set the two equal. It's effectively what we ended up doing. The potential energy in the spring is 0.25 joules, and that's equal to the kinetic energy in the system after it's fired, which would be 1/2 mv squared, solve for v, 2.24 meters per second. There was a lot here, so here's what I recommend you do. Work through this again, and set up this first line here with all these types of energy. And go through one by one, explaining to yourself and writing it out, why is the initial potential energy, gravitational potential energy, and the final gravitational potential energy, why do they cancel out? Why is our initial kinetic energy 0? Why are our Q 0? Why is my final spring potential energy 0? Prove it to yourself, explain it to yourself again, write it out. All right. And what it ultimately boils down to is that the spring potential energy in the system transformed into kinetic energy in the ball in the system. And we would just solve for V. All right. This question here was a little bit more difficult. Basically, it's now we turn it on its side. We actually fire it vertically. So the gravitational potential energy is a little bit, we can't just ignore it now. All right. So the initial potential energy in the spring is still the same, but all these other things go away. Look at all those things get crossed out. Well, the Q's get crossed out because we know that there's no friction, right? Well, let's go through everything else. The initial kinetic energy is still 0 because it still starts at rest. Like the ball is still held in the launcher at rest. Okay, think about what we did in lab. So the kinetic energy initially is still 0. The kinetic energy final is 0 because we're talking about the max height for the final position, right? So the final kinetic energy is 0 because the final velocity is 0. Now the potential energy in the spring final is 0 because the spring is no longer compressed. It's been fired, so that goes away as well. And the initial gravitational potential energy system is 0 because we're assuming it's launched at ground level. Now that's an assumption that maybe we can't always make, but for these types of questions, these simple like word questions, you can. Okay, notice in lab that we did not make it 0. Okay, that was the only difference in lab. So just watch out for that, but that was an assumption we made. If you didn't make that assumption, I would have to give you that value. Okay, or I would have to say, how high did it go above the muzzle or the nozzle of the cannon? All right. That way you would just make that height 0 anyway. All right. So effectively what ends up happening is similar to the last one. In the last one, all of our potential energy in the spring turned into kinetic. Now all of our potential energy in the spring is turning into gravitational potential energy to find the max height. And actually, I think this might be wrong. I don't think it's 2.25. I think it's actually, oh, here's the deal. I think I messed up the mass. I think the mass was 0.1. Yeah, the mass was 0.1. So there's actually a bit of a typo here. The mass was 0.1. So this is actually, again, I don't have my mouse, or my pen. So this is 0.1. Okay, so this is actually 0.255. So that's a bit of a typo. Let's just fix that. So these two questions were not easy by any means, but just work through them, reason them out to yourself again. If you go through them a couple times, they'll start to make sense to you more and more. But never cross out any of these energies saying that they're 0 without giving yourself an explanation. Okay, because on a test or quiz, I might say, give me the reasons why they're 0. All right. So if you practice like 2, maybe 3 times, you'll be an expert in it. No worries. All right. So always draw your pictures, always write out all of your types of energy, establish what's your initial picture, what's your final picture, and work from there. All right.